Here are some examples. This first series, the sum from n equals 1 to infinity of sine n over n to the 1.07th power. It's hard to understand what's going on with this series. We can't use anything like the integral test for a couple reasons. For one, it would be hard to integrate sine of x over x to the 1.07th power. For another, this is not a positive term series. When n is 1, 2, 3, 4, 5, 6, etc., sine of n is sometimes positive. For example, sine of 1, sine of 2, and sine of 3 are all positive. But sine of 4 is negative, and sine of 5 is negative, and sine of 6 is negative. Sine of 7 is positive, and so on. It's not even a very regular pattern, because it all depends on how many multiples of pi are less than n, or what largest multiple of pi is less than n. So some terms are positive, some terms are negative. It happens in a very strange way. It's hard to really tell what to do with this series. But if we consider the sum of the absolute values, we can compare that to a reference series just by looking at 1 over n to the 1.07th power. Because we have absolute values here, these are now all positive terms, and we can use a comparison test. And the absolute value of sine of n is a strange number for as n goes through all the positive integers, but it's always at most 1. So we can definitely say that sine n over n to the 1.07th power is at most 1 over 1 n to the 1.07th power. So these terms are less than or equal to those terms, and thus, by the comparison test, this series is convergent. Why? Because I should have mentioned this before. This is a convergent p-series. So let me state that again. I call this a reference series because it's a p-series. P is greater than 1, so it's a convergent series, and the terms of our new series are smaller than the terms of my reference series, which is convergent. So this series converges. So it's important for us to first take absolute values so we can apply the comparison test, then we get all the information we want. Now let's look at this new series. This is called the alternating harmonic series. I think I've mentioned it at one point in the past. It looks just like the harmonic series, only the signs alternate. We showed by the alternating series test that this series converges. And I'll remind you of why. It is an alternating series. Here we're starting with a negative term, but that makes no difference. We could multiply all the terms by -1 and start with a positive term. We're starting with a negative term, -1, then we're adding a half, then subtracting a third, and adding a fourth. The signs alternate, and the magnitudes of the terms, 1 over n, tend to 0 and are decreasing. Thus, the alternating series test applies, and the series converges. But if you take absolute values of each term, the sum of the absolute value of -1 to the n over n, you get exactly the harmonic series, which we already know diverges. So this is a series which converges, but the sum of the absolute values diverges. So we call this series conditionally convergent. Here's what's really interesting about the difference between conditionally convergent series and absolutely convergent series. It's a theorem which goes a little bit beyond the scope of our course now to prove that tells us if a series is absolutely convergent, then any rearrangement of the terms gives you another absolutely convergent series with the same sum. I apologize, let me fix this. With the same sum. So it doesn't matter how you rearrange the terms. You can rearrange them in any order. It's still going to be absolutely convergent. You still get the same sum. That's if a series is absolutely convergent. That would apply to this first series. However, this is not true for conditionally convergent series. And let me write down this series. The sum of -1 to the n over n equals 1 to infinity. This is the series -1 plus a half minus a third plus 1/4 minus a fifth plus 1/6 minus a seventh plus 1/8. This series converges, again, by the alternating series test. If you look at just the even terms, you'll see you have the sum of the reciprocals of the even numbers. That's each term is just 1/2 of, say, a term from the original harmonic series. Just the even terms diverge by themselves. And it should be pretty easy to see that if you take just the odd terms, all the negative ones by themselves, they'll diverge. So if I reorder the terms by adding up a whole bunch of odd ones first, take -1 plus -1/3 plus -1/5, and I keep going until I get the total sum to be less than, I don't know, less than -10. And then I add a single positive term. And then I keep going, taking more and more negative terms until I get back less than -10. And then add the next positive term. And then keep going like that. I'll actually have a rearrangement of this series that converges to -10. But if instead of -10, I picked -100, or if I picked any other number I want, I could get a rearrangement of this series to converge to literally any real number. So things are very strange for conditionally convergent series.